Thank you, Dean Julio. Dean Julio, thank you very much for that introduction, and thanks, Bill, for organising the day, and the school and the Sustainability Institute for hosting me. Certainly a pleasure to be here. I hadn't actually ever been to Chicago before, and I hadn't been to Northwestern University before. I've been in the academic world for most of my life, mainly in Australia, but also Stanford and Oxford and a few other universities around the world. Most recently I was at the University of Queensland, but for the last year and a half I decided to take the unusual step of leaving, as somebody said, the soft, cushy halls of academia and to walk into the environmental NGO world. I don't know which one is softer and cushier, but some people think this is soft and cushy. Having directed, having had 80 PhD students and 70 postdocs and raised about $120 million of external grants, I found it slightly stressful at times being in a university academic department, just sort of maintaining the momentum that people demand in terms of continuous funding, continuous grants, and supporting people. As you've heard, my background is quite odd. I was trained as an applied mathematician, but my true love is nature. I only did applied maths at the University of Adelaide because the zoology department was fairly useless, and I argued with them. I ended up doing biochemistry and applied maths. I ended up then going to Oxford, joining a department which I thought was about ecology, but it was a biostats department which was full of statistics, and I didn't know any statistics. And then I eventually ended up back in a maths department and finally an environmental science department. So I've wandered aimlessly between multiple disciplines. So some people think I'm an ecologist, some people think I'm a mathematician. I'd like to be an economist because they seem to solve problems and they know some maths, but the economists don't let me in. They say, I have no idea what I'm talking about, and that may soon be very apparent. What I'm going to do today is I'm going to skate across a lot of issues very quickly and just give you a flavour for what my interests are, but also some of the ways that the Nature Conservancy think. And even though I joined the Nature Conservancy as their chief scientist relatively recently, before I had joined the Nature Conservancy, I had co-authored 30 different scientific peer-reviewed papers with the Nature Conservancy, even though I was sitting many, many miles away. In fact, Australia did not have a branch of the Conservancy until about 10 or 12 years ago, and all my collaborations have been here with people in the United States, and that will be clear. So it was interesting. What struck me was that my group had developed a whole heap of decision science tools for conservation. So I was in a maths department. I ended up half in ecology and maths, and if I had one special skill, it was this, which is more or less the skill of an engineer or an economist, is tell me your problem. Tell me your problem. And conservationists have a lot of problems. Personal problems, you know. The biggest problem is their biggest problem is they wake up in the morning seeing the planet fall to pieces around their eyes. You know, if you care about birds, which is my personal bird watching, the rate at which birds are going extinct is roughly 1,000 times the normal background rate in the absence of an enormous meteorite or some other global disaster. So when you're watching that happening as you see it, it's very upsetting when tropical rainforests continue to disappear at about 0.5% a year. So conservationists have a lot of problems, a lot of anxiety, and they know that they're managing an incredibly complicated system. So the Nature Conservancy started dealing with that, and they were founded by the Ecological Society of America, so they were founded by scientists. They started working on land preservation. This was 1950s, before I was born. And they would buy, steward and protect land, and that was their modus operandi as they worked through the United States, buying and protecting land and handing it on to national parks. And that was being very successful. I mean, arguably 5 to 10% of this entire country has in some form of protection through various influences of the Nature Conservancy. So it's arguably a remarkable outcome. But in the last 10 to 15 years, 20 years as they've globalised, and now we're in 72 countries, they've realised that first of all you can't just keep buying land in other countries. China does not like a United States Green Group turning up and buying land. That doesn't go down so well. In many countries, acquisition of land is a very different proposition. The mechanisms, the protections, and so you have to work out how to change the system. And so that is the Nature Conservancy that some of you may have known from visiting one of their preserves, interacting with their scientists over the last long period of time, has changed enormously in the last 10 to 15 years to actually try and tackle the drivers of habitat loss, the drivers of species loss. Climate change. One of our 5 major priorities is climate change. One of our major priorities is to get natural climate solutions. How can we encourage changes to agriculture, forestry, from East Kalimantan to Brazil to occur to fix more carbon dioxide in the landscape? And we believe that 30% of the climate change solutions is a natural climate change solution, and that was published in PNAS earlier this year by our Natural Climate Solutions team. 30% of the whole problem can be solved just by reorganising how you manage forest and agriculture. So that's exciting. Some of our other, we still protect land and water, but we're also interested in building sustainable cities, and today we've been talking to Bill and others about that. So how do you make cities healthier, more environmentally friendly and more full of nature? Because I think what we're heading towards is 60% of the world will soon live in cities. It just keeps going up and up and up, and dramatically in places like China, the number of people in cities. So we're really trying to tackle the drivers. We're interested in food and sustainable food production. So you mean, why is the Nature Conservancy interested in food production? Well, if we can't improve food production, then people just keep destroying habitat so they can make more food. But if you can actually make food production more environmentally sustainable, better for climate, better for water quality, and higher productivity, then the pressure comes off the rest of the land and tries to slow down those massive deforestation rates that we see around the world, which are arguably the primary drivers of biodiversity loss. The only thing I'll say, and if you want to ask a question about population, I'll just say we have no position on population growth. There you go. Which is about, actually, of all the talks I've given in the 300 talks I've given in the last 30 years to audiences, is the third question is always, why are you doing all this stuff? If you can't stop people breeding, you'll never solve the problem. That's the driver we actually don't tackle. So you can ask the question, I'll just evade it, and it'll be a very awkward silence. So please don't ask the question. We don't tell people how many babies they can have, and we don't tell people how much food they can eat. So we tend to actually think that we have gone through an analysis that suggests that as the world heads towards about 11 billion people, we can have a win-win outcome. We can feed 11 billion people sustainably, and hopefully then it'll start dropping down a bit. We can get there, and it doesn't involve any more destruction of natural habitat whatsoever. Okay, so that's sort of the background to TNC and a bit of a background to me. And I'm just going to talk about some things that go all the way from policy all the way down to maths. And I always have to start these talks by pointing out I was in a university for 30 years, and as a good university academic, my entire life was built on the exploitation of others. And these are many of the others that I exploited. I've always had a very large lab of PhD students and postdocs, and those 650 or 700 peer-reviewed papers we've published are primarily because of them. So if you think, basically they do all the work, and I just take all the credit. It's all good. Let me just start off on one thing. Obviously, often people say university academics, they sit in their ivory towers, they write papers, and they don't engage. I engaged. At the age of 32, I was the nation's key biodiversity advisor to the federal government. And this is just one example of an engagement process. Queensland, which is the lovely state in which I now spend half my life, was clearing habitat 500,000 hectares a year. 500,000 football stadiums a year were being destroyed in Queensland in the 1990s and early 2000s. That puts us, Queensland, the state of Queensland, up there close to Brazil in terms of habitat destruction. And so when I was there, I actually got 400 scientists. I wrote a letter to the Prime Minister and the Premier. I sat on a whole heap of boards and committees. The letter basically said destroying habitat is bad for food, topsoil, water quality, air pollution and biodiversity. There was no new science. Got 450 scientists to sign it, and within 2 weeks the Premier of the state of Queensland was waving my letter, and he brought an end to that land clearing, and he brought it down from 500,000 hectares a year down to about 50,000 hectares a year, which saves around about 10% of Australia's greenhouse gas emissions. It's like the same as taking off half the cars in the country off the road. Okay, so I say that because I can say that and then I can fly around the planet forever and I have all these carbon credits. If you want to buy some carbon credits for me afterwards, I can show you. I can say that because you can have an impact. You just have to be at the right place at the right time. So, and you don't have to say anything interesting at all. The first person who pointed out that land clearing caused salinity in Australia wrote a paper, a scientific paper in 1924. So the one thing when you're talking to policy people, government people, politicians, is you're usually just digging up stuff that's 20 years old and writing in a very simple fashion and getting consensus across the board and delivering at the right time. And I'll tell you one last thing about that before I go on about policy. I could talk about this for 2 or 3 simultaneous talks. Why did it work? Why did the delivery of that particular declaration and letter to the Prime Minister and the Premier of the state, why did it have impact? Well, first of all, he was a left-wing Premier and the people in the country didn't matter to him because they never voted for him, so he could annoy the farmers, telling them not to clear their land. The second thing is he was just about to face a sex scandal in his parliament with one of his ministers and he wanted some smoke and mirrors. That is actually how many things happen. So it's like Jupiter, Mars and everything lining up. You've just got to get the alignment, and that's where some of the big NGOs are very, very useful. So we worked with them to deliver those outcomes. So it looks as though science delivered stuff, but it's actually all about luck and timing. But you've got to be ready. You've got to be ready to take your opportunity to deliver the science. You've got to deliver it very, very quickly. And that's true not just for people here, but it's also true for the Nature Conservancy. We're playing this same game. We're not a lobbying NGO. I think we have to only spend 1%, less than 1% of all our money on lobbying per se, but we do have to deliver information at the right time to the right place. So I just wanted to say that, policy is a way to get things done. Yeah, hi.
I have a question. As many people come to academia to avoid politics and social persuasion, how do you encourage people to get up on this is the art of persuasion.
I see. Because politics is annoying and there's a lot of people in it. And you stick your head above the ramparts and you get attacked. Most of the people who've ever attacked me actually have been members of the green groups because I didn't say enough or do enough. How do you do it? I just think it's my job. I just always thought that I should spend 20% of my life doing this stuff, which was helping government. And people often said, oh, you're wasting your time, they're not giving you any money. The federal government eventually delivered me $75 million of research grants over a period of 15 years that supported our entire lab, because for 10 years I just kept turning up to meetings, chairing things, sorting their problems out, advising them on legislation, and everybody says you're wasting your time, this is a day a week of your entire life, and they're not even paying you, they don't pay any attention to your advice. I can tell you it's like every other relationship. It takes an enormous amount of time, and all you have to do is just keep turning up. And there is no short-term reward, and also it's erratic and random. It's not like, well, NSF grants. what could be more erratic or random than NSF grants? Any granting cycle is random, but this is one thing where if you keep turning up, you'll get stuff done. So this next story is actually more about the science, but there's some political twists at the end. So I'm going to actually go into the maths of one of the things that I've done a lot of, but also the Nature Conservancy does a lot of, and that is all about how do you build protected area systems? How do you build protected area systems? And what is the science and maths behind that? They cover now 15% of the planet, the land and the sea, protected areas or national parks, if you like. So what is the problem? And early on, when people used to dedicate protected areas, they were places like Yellowstone, spectacular places, places where there was big wildlife, big forests, waterfalls and stuff like that. But then eventually in the 80s and 90s, a lot of American and Australian scientists decided, well, what are we really trying to do? It's not just a matter of here's a reserve, there's a reserve, we'll grab this bit. We actually want to have a system of protected areas. And that system of protected areas should equitably represent all habitats. And this is the trick, and we don't want to do it in a way that really annoys people. If you take a major fishing industry and put most of their fishing sites in marine protected areas, do you get a marine protected area system? You do not. So you've got to pay attention. You cannot, there's no point sort of fighting over the outer suburbs of Chicago where developers have already bought land and you say, no, this should be protected. That sometimes work in this country because of the Endangered Species Act, but in most places in the world, you just can't fight developers. So you've got to actually think about where you're going to go. So we had developed some software for forests, and we were working with the Great Barrier Reef Marine Park Authority, and they were looking to rezone the entire Great Barrier Reef. So most people in the 90s thought the Great Barrier Reef was the world's biggest marine protected area. It was not. It was not. Even though it's 1,500 kilometres by 300 kilometres, it's a huge, vast section of northeastern Australia. 4.7% of the Great Barrier Reef was not fished. So more than 95% of the Great Barrier Reef, which looked like a big green park, was fished. And much of it was trawled, not just surface fishing, bottom fishing. So they went through a process of how can we redesign this Great Barrier Reef Marine Park to actually meet the requirements here. This word problem. We want a connected, compact system. We want to represent all the habitats, and we want to do it in a way that annoys as few people as possible. So what does the problem look like? Well, first of all, you've got to divide this huge area into things that you are either going to be in or not in the protected area system. So there's 5,500 reefs. It's not one reef. There's 5,500 reefs in the Great Barrier Reef, and there's all these places between the Great Barrier Reef. So what do you think about? Okay, so we need to work out where all the species are, we need to work out where all the habitats are. Unfortunately, many marine ecologists have spent years assembling data on different fish, on different habitats like seagrass beds and coral reefs and different kinds of coral reef. And furthermore, they also had a fair bit of data about where people fished, recreational fishing and commercial fishing, trawlers. They knew where they fished. And this is important to know this because this is the social and economic side of conservation. If you ignore all this stuff, in fact they did ignore it for 2 or 3 years and they got nowhere at all. If you ignore all this, you don't get marine protected area systems. So we're now combining ecology, maths and socio-economic information. And then you stick a grid on top of it and what do you end up with? Something like this, which is a matrix. Now we're happy now. Actually, I should say, who here is sort of feel as though that they're an engineer, applied mathematician, and that sort of, who is more of a social scientist maybe? Some social scientists? Who's more of a ecologist, biologist? Who wishes they were in another room and don't know why they turned up? So anybody want to call that another random discipline, computer science? Anyway, so okay, it's a good mix actually. I like the fact we've got about a third, because hopefully I'm going to keep you all equally annoyed. So this is the kind of data you have, and this is all about problem formulation. We know there's different types of habitat, and I'm not very good at marine ecology. We know we have some places, and each place we know, and this is the toy Mickey Mouse reserve design problem. the toy Mickey Mouse returns a problem, we just know if the thing is there. So Nemo is in sites A, C and D, but not in the other sites. So the first little toy game is this. I just said, find me a set of sites that represent every one of these things I care about, then you could just say, I'll have every site. I'll have all 8 of them. All 8 of them. Grab them all. That's easy. Get everything, because they're everywhere. Everything is, this is how many sites they're in, I'll get everything. But then you said, actually no, that's going to annoy everybody if you make the whole Great Barrier Reef as a big no-take area. So why don't we do it in a way that annoys people as little as possible, and we'll assume the cost of every site is the same in terms of annoyance. Find me the smallest number of sites that represents all the species, and you say, oh, that's easy. The answer is, what's the answer? ABC. A gets me those 8. That's a good site. That has lots of species. Let's grab that. And then I'm missing this tern feeding area, and I don't even know why I like sharks. I hate them, but I've got to preserve them. And they're threatened, so I'm conserving them. Is that the most efficient answer? Well, I wouldn't have put it up if it was, would I? Yep. No, not yet. This is the baby problem, and you're going to the full problem. But yes, you could. You can, and these can be all areas. They can be targets. The interesting thing is that even this tiny problem is not as obvious to solve as you might think, because the best answer is C and E. You can save everything with 2 species. Okay. So why is this an interesting problem? Even when we do the real problem has 250 rows. It has 17,000 columns, 17,000 places, 250 features. These aren't zeros and ones, they're areas. The cost of every site is different. We're interested in connectivity and potentially species interactions in terms of keynotes. So we've got an incredibly, even when you write down the simplest possible problem, and the interesting thing is the ecologists had been solving this for years, and their algorithm to solve this problem, conserve everything as cheaply as possible, their algorithm was grab me the site with the most species. Then add what I can to grow as quickly as possible. So I'd add that. These are all covered. Now I just add this and this. Doesn't work. In fact, you're 50% inefficient. This is going to cost you hundreds of millions of dollars, this mistake. And you say, okay, well, maybe I could have come up with another algorithm, and they invented more algorithms. The trouble is, they didn't realise that engineers and applied mathematicians and economists have been solving this problem forever. It's called an integer linear programming problem. And they've been working on it, well, particularly during the Second World War, in an attempt to kill the enemy as fast as possible. Integer linear programming, runs half the planet, doesn't it? It's picking sites to maximise outcomes or minimise costs. And so they actually spent 20 years in the ecological literature solving an ill-defined problem. Nobody wrote the mass of the problem down with algorithms that they just invented. It was quite logical. They're not stupid people. They were smart. But they could have asked a mathematician or an engineer. And of course, yes, there's a moral in this, the greedy is. And what they didn't realise, and this is, I suppose, all about complexity theory in some senses, the whole is never the same as the sum of the parts in any ecological world. That so many ecologists and conservation scientists have solved problems, and the only tool they have is adding. Everything's linear and everything's added. What is the maths of the problem? The mathematical problem, and we have a piece of software that solves this problem, is minimise the cost of the system. So there's a control variable for every site, and it can be 0 and 1, so there's all the control variables. So every site is either in or out of the reserve system. We want to meet all our conservation targets. We take that matrix R, which was the matrix you just saw. We have some targets. Now these can be areas. The targets don't have to be 1. They could be 3,000 hectares of seagrass or 200 fish. And then we want to do it in a way that minimises the cost of the whole system, and we want to do it in a way that makes the system connected. Okay, so that's the problem that we write it down mathematically. All we've done there is turn that paragraph of words, get me a bit of everything in a compact connected system to annoy as few people as possible, and we turn words into maths, which is modelling, or arguably it's not it's translation. There's no real modelling there. This is just, you know, when everybody told you when you were in high school that maths is not a science, maths is a language, and you thought the person's crazy. Maths isn't a language, maths is science. Maths is no more science than arts. This is a process of translating humans' hopes, dreams and fears into some equations. And once you do that, of course, you can bring to bear all the power of hundreds of years of mathematics to solve those sorts of problems. So that's what we did. And we produced a piece of software called Marxanne. You can Google it. It's a Wikipedia thing. It's actually an algorithm, not a model. I always think of that thing as a problem, not a model. And it solves a problem. This piece of software, which was half of one of my PhD students' PhDs, has built half the protected area systems in the planet in the last 10 years. Half the protected area systems in the entire planet.
So I would think you would need to add some risk or vulnerability to that.
Oh yeah. We have a version called MarProb, P-R-O-B, that adds that. Yeah, yeah. So this is still, again, the toy version, and it gets complicated. And then it's a whole family of software tools that add into some of the complexities we're talking about. The interesting thing is, why is this now used by most countries to build their help build your California marine protected area systems, helping Canada design its entire EEZ is protected. Why? Because we gave it away for free, believe it or not. That's the primary. It's not very good. It's clunky. It's straightforward. This is very simple integer linear programming. You would have fourth years who could program this up. We use simulated annealing. It's not even the most clever algorithm on the planet. We documented it. We wrote papers with it. And we distributed it. And that's actually also, TNC was the major user. They built all their half of their ecoregional plans using this software. And so it's simple to understand. TNC now, one of our big businesses, is actually providing people with tools. So whether it's land developers, Dow Chemical, we give them tools on ecosystem services. We're actually, one of our major activities is delivering tools. And of course that's the maths, the problem definition, and also the software. And the key about these tools is they're easy to understand. They're not too black boxy. This is a bit black boxy. It's not too black boxy. And this is the sort of the politics. The interesting thing is, of course, 17,000 planning units. These are all the zeros and ones. I often ask when I'm giving a public lecture, I say, well, how big a problem is that? Why couldn't we could have spent longer. We would have got that first one. We would have got C and E eventually. How hard can it be? How many possible solutions are there? It's 2 to the power 17,000. Oh, I can write on a chalkboard, excellent. Having done maths lectures for years and years, I always miss the opportunity to write on a chalkboard. 2 to the power 17, because every one's in or out. So every, and what's that, well, in terms of a ridiculously bad approximation, that's that. Which, and I gather somebody told me the number of protons in the universe might be about 10 to the 80. Is that right? Plus or minus 1. So we've created a tiny little word problem that turns into a tiny little maths problem that has so many solutions. It's a bit like every proton in the universe having a universe in the proton. And if you set all the computers in the planet running just mindlessly iterating, if you didn't have smart search algorithms, so this is my attempt to convince ecologists and conservationists that mathematicians and engineers may well be useful because they can get you good answers to that sort of problem and make it easy to understand. There was, again, a pathway to policy. A lot of it was about transparency and these marine protected areas don't get done very quickly and they don't get done very well, and I'll show you that in a second. So it all sounds very simple, doesn't it? Ecologists get data, mathematicians and engineers sort the problem out, they deliver a plan to the government says, great, this is a good idea, here's a marine protected area. and everybody's happy. There's more fish, the fishermen are making more money and all those things. It never works like that. There's no Hollywood version of this movie. This one was a Hollywood version. So we got the whole Great Barrier Reef rezone and it went from 5% protected to 33% protected. The fishing industry, even though they hated us at the time and sent me death threats, are now making more money than they ever did. The tourism industry is making more money. It's a little bit sad that Great Barrier Reef is being bleached by climate change and coral bleaching, but the bottom line, we've done what we can to give it the best possible start. So it's been used successfully in a lot of other places. It's relatively simple decision support tools, simple and logical. Let's now stay in the same country, Australia, which is supposedly civilised and intelligent, and wonder, here's the Great Barrier Reef Marine Park, here it is. Again, don't remember this is 1,500 kilometres long. This is a vast area. At least that's the coast of California, more or less. And then we started building another protected area system, which is the entire exclusive economic zone. And this is a protected area system that is trying to conserve components of an area that is the size of the entire continental United States, 9,000 square kilometres, 3,000 square miles. And this is the proposals they've had, and they put them up in about in early 2000s. They still haven't been declared. They still can't get through Parliament. They're being argued about. And not only have we taken 15 years and we still haven't got the reserve system worked out, if you look carefully at the reserve system, you realise it breaks all the rules that I just talked about pretty well. So this is the northwest of Australia. This is an incredibly remote area of Australia. We trained the Commonwealth Government in the use of our software. They had a lot of data about different habitat types, different fixed species, where fishermen went, where the oil and gas industry were interested in going. And this is the reserve system they've ended up proposing. And what's that? There's a big reserve there, and that's conserving something that's dark blue, which is the abyssal plain. So we've conserved 85% of the abyssal plain. And there's all these other ecosystem types on the shelf. This is all the shelf, which is less than 200 metres deep. This is 4,000 metres deep. This is 200 metres deep. What have they done? They've just made a reserve system that meets all our international agreements about conserving 10% of the ocean, and they've done it in a place which basically wasn't under threat to anybody by anything. You don't usually trawl at 4,000 metres. We don't yet dig up oil and gas at 4,000 metres. Well, we don't yet. How could that piece of software that I just talked about produce this outcome? It can't. If we're conserving 10 or 20% of every habitat type, we can't get zeros here. So you can do all the science, you can do all the decision support, you can do all the politics, and in the end, the politics wins. And why? It's oil and gas. So I think you have a government now that's slightly enthusiastic about energy and appears to like oil and gas and other things. If you actually map, this isn't a full map, all the different gas and oil leases, it basically covers all the shelf. And so the Australian government decided that regardless of how much science we had, they were not willing to forego a single cubic centimetre of fossil fuel. So we can be bad too. In the end, bottom line, all the maths and all the science doesn't really necessarily get you to an outcome you want. And there's a whole heap of other happy examples, there's sad examples, and there's everything in between. The last thing I sort of want to talk a bit about, sort of to, again potentially to provoke discussion, and then I'll talk a bit about some of TNC's stuff, is this is the talk I give, which basically tries to annoy as many scientists as possible. And I ask the question from a perspective of the Nature Conservancy or any other big environmental organisation: what science is useful? What science is useful? And at the moment, in fact, we're more and more using economics and social science and human values and a whole heap of other sciences. Classic science we're using less of. And I ask this example because it boils down to the issue, a lot of people say they're doing conservation science, and the literature in conservation science is now huge. There's 40 journals. The best impact factors of conservation journals are around 7, 8, 9 and 10. So They're very high impact journals. Is all that science and are all those papers useful? So I always happened to be in Scotland, and I was at St Andrews, and I was giving the talk before the final dinner, a plenary, and during the conference I'd heard several talks about puffins, and of course puffins, most adorable bird in the planet, and many of the people giving talks in Scotland they'd been given a whole heap of money, £1 million, £1 million British pounds, to design a perfect monitoring strategy to see whether or not that puffins were in decline because of climate change. So they had a null hypothesis, puffins are okay. And they wanted to do a nice power analysis to survey the islands in different ways to maximise the chance they could reject that null hypothesis if it was not true. Classic type 1, type 2 null hypothesis testing work. And they gave brilliant talks, great statistics, all this power analysis. You know, when you learn power analysis, it hurts your head. It was excellent stuff. And so they gave, and in my plenary, I started my plenary talking about this, and then I said, why? Why? What are you going to do? So the puffins are in decline because of climate change. Are you going to give them all a fridge to keep them cooler? Are you going to hand feed them sand eels? What are you going to do? They said, oh, that's not our problem. And that is their problem. Spending £1 million of conservation money answering a question for which there was no obvious action makes me a bit anxious. And that is a little bit of the story of much of conservation science. We can't afford to do that anymore. Anyway, they were a little bit annoyed. So at the dinner that night, it was at St Andrews, you know, the golf course, nice country club, and I was sitting there with my wife alone. Enough of them had enough whiskey to come up and chat to me and say, Hugh, we don't like your plenary talk, we're annoyed. But we actually can't, we've been thinking about why we're doing this. Well, you should have thought that before you started spending £1 million. And we now think that what we should do is, if we can prove that puffins are in decline, we now know that Svalbard and Greenland are going to be the places where the puffins are going to survive. So we have an action. I said, well, that's good, you do have an action. But if the action is, write a letter to Greenland, dear Greenland, our puffins are disappearing, could you look after yours? Then the action may be so low cost, you may as well do it anyway. We think there's a chance we're losing our puffins. We really think we should invest in conservation of puffins in Greenland. So sometimes there's no action. There's no need for science. Sometimes you have to find it. You might have to invent a way of saving puffins. Sometimes, but just documenting decline has been one of the biggest disasters of conservation science and ecology. We have just documented disaster without actually thinking, what is the science? You don't need to prove anymore that the world's in a mess. Everybody knows the world's in a mess. Species are going extinct 1,000 times a background rate. We need the science we need to know to make an action. So what I've been doing with the Nature Conservancy, but also in conservation in general, is to really thinking about how do you prioritise research? What is the most important research questions? It's not giving money to the person who has the biggest H index. It's not the most intriguing question. That it actually needs some thought to value of information theory. Who actually thought much about, has done a formal value of information theory analysis? And basically, I'm not going to go through the formal analysis. It's really mathsy. But the question first is, could a new action happen? Do you have choices in the actions you're taking? If there's no choices, do what you're doing. More. Is there a chance, if there are multiple actions that you could be taking, you know, should I be putting up nest boxes for this little bird, or should I be planting more trees? If there's multiple actions, is the research you're doing likely to change the action you're taking? Is the research likely to change the action you're taking? And then finally, this is the really nasty one, is the expected improvement going to be bigger than the money and time you spend on the research? And maybe that's the hardest bar of all. But from my perspective, I'm in the Nature Conservancy, we have a $700 million budget a year, of which probably 10 to 15% goes to science. I don't control it all. of that $100 million that we're spending on science, how can I argue that that is delivering more than spending another $100 million, all of that just doing stuff on the ground, buying more land, reforming more fisheries? So this is sort of my analysis, and this is the thinking that I like to get people to go through, is you have a strategy and you can deploy it, and the benefit of the strategy is here on the y-axis, and as always, science is all about removing uncertainty. We're either understanding a process or we're refining our knowledge of a parameter. I mean, this is a very simple example. Let's say there's something we don't know about the species. We don't know how much Arctic foxes are eating puffin eggs in some place. And there's uncertainty about a parameter, and we also know that the strategy we're taking, so we do have an intervention strategy, the strategy we're taking, its performance varies with the unknown parameter. And usually for most scientists that's enough for them to say, oh, I really need to tighten up these confidence intervals because I really want to know how well I'm going to go. The first question is, if that's the only thing you can do it. In the puffin case, there wasn't anything they could do, so don't do that. So rule one, if there's only one thing you can do, there's no need for research. The research might be finding another thing to do. Then if there's another strategy, 2 or 3 or 4 strategies, but whether one is better than the other doesn't matter on your knowledge. So you just do a sensitivity analysis around this parameter or this process, and you find out that strategy B is always better than A. Well, I don't care about that parameter. In fact, it's the parameter, it doesn't have to be the parameter with the most uncertainty is the one you tackle first. So just do B. And then you might say, well, that's not very interesting. What happens if B and A deliver different outcomes depending on the parameter? So if the parameter's over here, A is better. If the parameter's over there, B is better. But in the end, the difference is so tiny. So this often happens in our reserve planning work. There's millions of solutions. It's like a plateau of optimisation. And almost everything on this huge multi-dimensional plateau is so close to each other. The best thing to do is give the policymakers lots and lots of different alternatives and not worry about, I mean, optimisation people can go crazy. They're looking for 1 or 2%, when in the messy world that is ecology and conservation, 10 or 15% is the things you really want to worry about, not 1 or 2%. And so in this case, no, again, you don't need more science. You don't need more knowledge, because the benefits, the costs of refining this probably don't weigh out the benefits. And this is the interesting situation. And this is where science is important. And so I'm trying to encourage all my colleagues at the Nature Conservancy to make sure that every time they do some science, it's tied to a narrative that connects the science and the knowledge to the choosing between the actual actions they deliver. Or, what I haven't, is developing a new action that they hadn't otherwise thought of. You know, there may be a strategy C. If your science is doing that, then that's interesting. That mental process rarely seems to penetrate into the conservation science literature. And we have a whole heap of examples of that. In fact, we were writing value of information papers when we didn't know what value of information was. And maybe it's just because I'm cynical and bitter and twisted. I was asking questions about, you know, how much data do I really need to know on where the beetles are? We've done some global analyses of where important conservation issues are, and we did it based on birds and plants. And as soon as you publish that paper, the beetle people and the frog people and the moss people get very, very anxious. And they say, your map of global priorities for conservation is rubbish because you didn't put the beetles in. So then we find a group of beetles and we put them in, and we find it makes about that much difference. You know, Madagascar, Solomon Islands, Borneo, the Northern Andes, those places are important for conservation by everybody's measure. You can change the taxa, you can change the processes, they're always fundamentally important issues. Anyway, we've taken this theory of optimal knowing and we've looked at weed eradication, we've looked at managing harvestable populations, we've looked at how much data do I need? Every time I talk about the Great Barrier Reef, somebody says, well, that's all very good for the Great Barrier Reef, but I live in Gabon, and Gabon hasn't got 1,000 marine ecologists. I say, well, maybe you don't need them. Maybe you need a map of bathymetry and water currents and a little bit of remote sense data, and maybe we can build a bit of a marine protected area sense in Gabon that makes some sense, which will do for now. Don't wait for 30 years to gather more information, because by the time you've got there, the international fleets will have pillaged Gabon and there will be no fish left. Well, they've actually half done it, I think. So how long should you wait for new data is also critical. And there's a whole heap of papers, and I'm happy to leave my slides behind on those issues. And lo and behold, we actually found that the people at US Geological Survey were much better than this than us, and they've been thinking about value information theory for longer, and they actually did it all much better. Anyway, that's by and by. Okay, I'm going to end with this slide, which is my slide of life. Okay, so a lot of people make conservation very complicated. They make natural resource management very complicated. They write books about it. So the Nature Conservancy has a new guiding document. It's called Conservation by Design 2.0. You can Google it, and it's free download. And if you get the Conservation by Design 2.0, Randy here from TNC has read it, and he knows, he tells you what's in paragraph 3 on page 74. Yeah, exactly. That's right. That's how it starts. You bet. So this is like the Nature Conservancy's Bible. There's 104 pages about how do you make good decisions. So we're actually trying to turn a lot of land managers and conservationists into people who think a little bit more structured way, like engineers and social scientists, about solving problems. But in the end, I think it's that. It's 31 one-syllable words. And that's actually all you need to know. You don't need to read the book. We had it before with that problem definition. What do you want? I want to save a bit of everything. What can I do? I can make marine protected areas. How does making marine protected areas affect my fisheries, my conservation outcomes, how much I annoy people? Which places do I protect? Do it. And then, this is the bit actually, of course, we sadly in natural resource management, this is the bit where we're struggling with. Do all this stuff, and of course when you're doing stuff at scale with protected areas and water funds and reorganising fisheries, the learning loop is really slow. If this takes 10 years, learning is hard. It's nice to learn about something like Rubik's Cube, where you can fiddle with it and you can get information in about 25 seconds. Learning about the impact of rezoning of marine protected areas on the world is much slower. Anyway, so my challenge, I suppose, at the Nature Conservancy is we're trying to save the planet. We have 350 scientists. We publish 0.1% of all of the environmental science in the world, by my calculation, 0.1%. That sounds like a lot, that's good. It's probably basically what you guys publish every year. So we need friends. And so part of this visit is actually we're 1,000th of the solution to the science problem, so we're trying to make as many friends with as many universities as possible and get you solving as many of our problems as possible, and us delivering, and we have an infinity of problems, delivering as many of our intractable problems to you as possible. So Dawn and I are here talking about some of our programs. We have postdoctoral programs, we have SNAP working groups. SNAP working groups are work at Santa Barbara, where groups of scientists come together to solve the most difficult natural resource management problems we have. We're hoping to build more relationships. The local chapter here has a number of relationships with this university. So how can we actually make... The moment TNC's relationships with universities are very much the whole is the same as the sum of the parts. What we're trying to do, and I suppose my job is, and Dawn's job and Cassie's job, is to make this series of relationships more than a whole string of random one-night stands. So we're interested in marriage. Let me put that clearly on the table. So we're interested in a more permanent relationship. We would acknowledge that we're polygamous. So we do work with other universities. I don't want you to get upset if you see us out with Cornell or Stanford some night on the town. But the bottom line is we need a wide range, and we're looking to have more permanent institutional arrangements. And I think that this university and this faculty has a whole heap of the skills that we need. Thank you very much.
Thank you.